Think about the prompt you sent to an AI chatbot. The words you type never enter the model. Before the transformer performs a single computation, your prompt is converted into a sequence of numerical tokens. From that moment onward, the model operates entirely on numbers. It never processes your sentence as English. It processes it as a sequence of token IDs. The system responsible for that conversion is the tokenizer. Although it often receives far less attention than the transformer itself, the tokenizer plays a fundamental role in every large language model. It defines the model's vocabulary, determines how text is segmented, influences computational efficiency, and affects how well the model handles different languages, domain-specific terminologies, and previously unseen words. Understanding the tokenizer is the first step toward understanding how large language models process language. Let's start with the large language model. A large language model is a neural network trained to understand and generate text. Models like GPT, Llama, Gemma are all examples. But a large language model cannot process raw text directly. Neural networks operate on numbers, not words. So before any computation can begin, text must first be converted into discrete numerical units called tokens. This conversion process is called tokenization. Let's consider this sentence. Large language models are powerful. To us, this is a text. To a tokenizer, it's an input sequence that must be segmented and numbered. Once tokens are identified, each one is mapped to an integer from the model's vocabulary. These numbers carry no meaning on their own. They are simply identifiers indices into a lookup table. The meaning comes later, during the embedding stage. Think of the tokenizer as defining the vocabulary of the language model. Everything the model processes is expressed in terms of these tokens. We have different types of tokenization. Let's start with the character tokenization. This straightforward approach treats every character as a token. For example, the word hello is split into individual characters. The vocabulary of character tokenization is tiny, just letters, digits, punctuations, and a few special symbols. Any word can be represented, even words that the model has never seen before. But this simplicity comes at a cost. The word internationalization becomes more than 20 individual tokens. Longer sequences increases the computational cost in every transformer layer which processes every token at every step. More importantly, individual characters carry almost no semantic information. The letter A tells the model almost nothing about meaning. The model will have to reconstruct entire concepts such as words, phrase, ideas from single letters, making training far harder. For these reasons, character tokenization is rarely used in modern language models. Another tokenization we'll be looking at is word tokenization. This idea seems more natural. Instead of splitting text into characters, it's being splitted into words. We have the sentence, machine learning changes everything. It's being splitted into individual words. Each word becomes one token. Sequences are much shorter. This aligns more closely with how humans think about language. But word tokenization introduces a different problem. Natural language contains an enormous number of distinct words. Let's consider this variation: work, working, worked, worker, workers. Should every form have its own vocabulary entry? What about names, technical terms, misspelling, or words that didn't exist when the tokenizer was built? The vocabulary goes without bond, and eventually the model encounters words that simply are not in it. These are called out of vocabulary words. When a tokenizer has no entry for a word, it cannot represent it at all. For example, let's ask an early word tokenized model about COVID in 2019. It should have had no entry for that word, not even an approximation. The token simply did not exist. For modern language models, this is a fundamental limitation. Now, let's look at another tokenization, the subword tokenization. Modern language models solve out of vocabulary using subword tokenization. Instead of treating a whole word as one token, the tokenizer learns smaller reusable pieces of language. Let's look at the following examples. Unbelievable is split into unbelievable. Playing is split into play and ing. Happiness is split into happy and ness. The tokenizer is not memorizing every possible word. It's learning building blocks that can be combined to form many different words. This has a deeper advantage beyond vocabulary size. Let's consider these four words: play, playing, played, player. All of them contain the subword play. Because they share the same token, they all activate the same learned representation for that concept. The model doesn't have to learn the concept behind play 4 separate times. It learns it once, and that knowledge transfers automatically to every word that contains it. This is why subword tokenization is not just a practical compromise, it's a structural advantage. Virtually every language model uses some form of subword tokenization. The exact algorithm differs, but the underlying underlying idea is the same. Now let's look at how subwords are chosen. An obvious question is, how does the tokenizer decide which pieces become tokens? It doesn't rely on linguistic rules written by hand, it learns from data. The process has two phases. First, you train the tokenizer on a large text corpus, then you freeze the vocabulary and use the tokenized input for model training. During tokenizer training, the algorithm analyzes billions of characters and identifies sequences that occur frequently together. Common combinations gradually become individual tokens. The starting point is always the smallest possible unit, individual characters, or in some cases, raw bytes. From there, different algorithms take different approaches. Let's look at 3 different algorithms used for subword tokenization. The most widely used algorithm is the Byte Pair Encoding or BPE. It was originally a data compression technique, later adapted for NLP. Here's how it works. Let's start with a corpus of text and split every word into individual characters. Each character is a token. Now count every adjacent pair of characters across the entire corpus. Suppose the pair character E and character S appears most frequently. Merge it into a single new token. Count again. Now character ES and character T is the most frequent pair. Merge it into EST. Repeat this process. Count the most frequent pair, merge it, update the vocabulary until you reach your target vocabulary size. Words that appear often in training data will gradually merge into single tokens, where combinations stay as smaller pieces. The result is a vocabulary that naturally reflects the statistical structure of the language it was trained on. GPT-2, GPT-3, GPT-4, and many other models use BPE, specifically a variant called byte level BPE, which starts from raw bytes rather than characters. This guarantees that any input in any language with any character can always be represented. There are no unknown tokens. Another algorithm is WordPiece. WordPiece was developed at Google and is used by Beth and many of its descendants. The high-level goal is the same as BPE, learn a vocabulary of subwords from data, but the magic criteria is different. BPE merges the pair that appears most frequently. WordPiece merges the pair that maximizes the likelihood of the training corpus. In other words, the merge that best explains the data statistically. In practice, this means WordPiece tends to be more conservative with its merges. It prefers splits that keep linguistically meaningful units intact rather than following raw frequency. You can see this in how WordPiece represents subword. Tokens that appear in the middle of a word are prefixed with hash to mark them as continuations. For example, unaffected is split into on, then double hash with affect, then double hash with ed. This makes it explicit that double hash affect is not the word affect on its own. It's a piece that follows something else. WordPiece is particularly strong on morphologically rich languages, where word forms are built from many small, predictable pieces. Another algorithm we'll be looking at is the SentencePiece. Both BPE and WordPiece assume that text and recipes split into words separated by spaces. That works for English, but many languages don't use spaces the same way. Japanese and Chinese, for example, don't separate words with white space at all. Applying a space-based tokenizer to these languages will produce incorrect space from the very beginning. SentencePiece, developed at Google, solved this by treating the input as a raw stream of Unicode characters with spaces included. Rather than splitting on white space, SentencePiece treats a space as just another character and learns how to handle it from data. The underscore character is used to mark where spaces appear. For example, hello word is split into underscore hello with underscore word. This makes SentencePiece language agnostic. The same algorithm works equally well on English, Japanese, Arabic, and any other language without needing language-specific preprocessing. SentencePiece can use either a BPE or a unigram language model as its underlying algorithm, making it more of a framework than a single fixed approach. Llama, Gemma, Mistral, and many other multilingual models use SentencePiece for exactly this reason. Now let's look at how a tokenizer is built. To build a tokenizer, there are 5 steps involved. Step 1. Collect a training corpus. You gather a large, diverse text dataset, ideally one that reflects the kind of text the model will process. If you are building a multilingual model, you include text from many languages. If you are building a coding model, you include large amounts of source code. Step 2. Choose a vocabulary size. You decide how many tokens the final vocabulary will contain. This is a deliberate trade-off. Large vocabularies produce shorter sequence but require more parameters. Smaller vocabularies are more efficient but produce longer sequence. Most modern models land somewhere between 32,000 and 120,000 tokens. Step 3. Run the merging algorithm. BPE, WordPiece, or any other algorithm begins from individual character or byte and repeatedly merges frequent pair until the vocabulary reaches the target size. Step 4. Add special tokens. Once the core vocabulary is built, special tokens are added manually. Beginning of sequence, end of sequence, padding, and any tag-specific markers that the model will need. Step 5. Freeze and save. The vocabulary is fixed. From this point forward, every input to the model during training and at inference is tokenized using the exact vocabulary. It never changes. An important point to note is that the tokenizer and the model are trained separately. The tokenizer is trained first, its vocabulary is frozen, and then the language model is trained on top of it. If you later want to expand the vocabulary so as to add a new language or new domain-specific terms, you have to either retrain the tokenizer from scratch or fine-tune the model on additional tokens. Let's look at vocabulary size, token IDs, and special tokens. Every tokenizer has a fixed vocabulary, typically somewhere between 32,000 and 120,000 tokens. The vocabulary size reflects a deliberate trade-off. A larger vocabulary produces shorter sequence, which reduces compute in the transformer, but it also means a larger embedding metrics and more parameters to train. A smaller vocabulary keeps the model lighter but produces longer sequence. Tokenizer designers pick a size that balances these periods for their use case. For the token ID, each token is assigned a unique integer. Every tokenizer also reserves a set of special tokens. These are markers that structure the model's input. Common examples include beginning of sequence, end of sequence, padding for batched inputs. Chart models often add markers like user or assistant to separate tones in conversation. You will see this when you inspect a real model's tokenizer config. Token IDs are not embeddings. They contain no semantic information. They simply tell the model which row to retrieve from the embedding metrics. We will explore that in the next video. In summary, what makes subword tokenization powerful isn't any single design choice. It's the balance it strikes. Small enough vocabulary to train efficiently. Large enough coverage that almost any word in almost any language can be expressed. And because subwords are learned from data rather than written by hand, the pieces that emerge tend to track real linguistic structures such as roots, suffixes, and common phrases. The tokenizer doesn't know grammar, but frequency does a surprisingly good job of approximating it. To summarize what we've covered, tokenization converts raw text into discrete integer tokens before anything else happens. Character tokenization produces tiny vocabulary but very long sequence with little semantic signals. Word tokenization aligns with human intuition but collapses when it encounters unseen words. Subword tokenization balances both by keeping vocabulary manageable while allowing any word to be expressed and enabling knowledge to transfer across related words through shared tokens. BPE builds its vocabulary by repeatedly merging the most frequent character pair and is used by the GPT family of models. WordPiece uses a likelihood-based criteria instead of raw frequency and tends to preserve more linguistically meaningful units. SentencePiece treats text as raw character string with no assumption about white space, making it language agnostic and the foundation for most multilingual models. A tokenizer is trained once on a large corpus, its vocabulary is frozen, and the language model is then trained on top of it. In the next video, these token IDs will enter the embedding layer where they stop being arbitrary numbers and become geometric position in the meaningful space. If you have any question, you can ask in the comments. Thanks for watching.